Hello everyone, my name is Shoman Dash and I will be presenting our work titled GCA-Net Utilizing Gated Context Attention for Image Forgery Localization and Detection. This work was carried out in collaboration with my co-authors Mohammad Saiful Islam and Mohammad Ruhul Amin. In the past few years, there has been overwhelming increase in the generation or synthesis of forged media content owing to the development of deep learning-based manipulation techniques. For the purposes of our work, we are classifying image forgery into two groups: manually forged images or photoshopping and deep learning based forgeries. Although defects are receiving quite a lot of attention, manual forgeries are still very prominent due to their ease of creation and availability of advanced image editing tools. As such, these forgeries are still quite difficult to identify reliably. In this work, we will focus on three main types of forgeries: copy move, splicing, and inpainting. In copy move, some part of the image is copied and pasted onto the same image in a different location. Splicing involves two separate images where some region is copied from a source image and pasted onto the target. Finally, in inpainting, some part of the image is removed by repainting the pixels by estimating the background data. Over the years, a large number of methods have been proposed in order to detect and localize these manipulations in images. However, there are some common drawbacks to these existing techniques. Existing neural network pipelines are designed as end-to-end sequential architectures which suffer from local bias. One of the main aspects of image forgery is that the signature of the forged region is different from the remaining background. We need to utilize this contrast between local and global feature groups for better forensic understanding. Consequently, these forensic traces are very minute and will get attenuated due to the gradient loss as they are passed through multiple sequential layers. This can be overcome through the use of cross-layer communication and feature propagation. Thirdly, existing methods make their predictions on a pixel level by classifying each pixel as an individual data point. However, this results in a lot of noisy predictions and false positives. Pixel-level prediction fails to utilize the difference between forged boundaries between local and global clusters. Moreover, since these methods base their classification on the degree of localization threshold, they suffer from inconsistencies when faced with unseen forgeries. Lastly, by definition, authentic images do not contain any forged content. So when the existing networks are faced with such images, they predict erroneous pixels and false positives. This happens because they are trying to identify each individual pixel as forged or not. Thus, with low precision, false positives also increase. The figure shows predictions on a few existing networks when tested with different untampered images. Their predictions are very noisy, with a lot of background pixels being labeled as manipulated. So, in this work, we have tackled four major points: reducing false positives for untampered images, reducing the local bias of sequential networks to improve the spatial and group understanding, solving the problem of feature attenuation through sequential layers, and also improving network robustness for real-world inference. Our proposed solution is the Gated Context Attention Network, or GCA-Net, which is a dense encoder-decoder network composed of gated self-attention layers for improved feature understanding and forgery localization. This is the overall architecture of the network. There are two main portions in this framework: a content suppression module that fuses multi-domain features from the input, and a segmentation module for classification and segmentation. We use an EfficientNet B4 backbone for the encoder and a UNet++ decoder for localization. The green squares are part of the encoder backbone, and each gray circle is a decoder module. The input goes through each layer to produce a final localization output as well as a classification label. Now let us look at each part of the network independently. The input first goes through four individual modules to generate some features. Each module here extracts a different feature from the image. These features are all concatenated to result in the final input domain features. These blocks are used to separately extract signal features and suppress the spatial data. For image forensics, we need to identify hidden distinctive features from images. Due to manipulation, the signal characteristics or compression levels of an image change. We use the signal features in addition to the input image for better classification. Alongside existing steganalitic features, we introduce a new error level analysis module that uses the difference between compression levels to generate a feature map. Next, this combined feature goes through the encoder backbone. We use EfficientNet B4 backbone. From the backbone encoder, we select 5 stages of intermediate features that correspond to 5 different scales. The use of these multi-scale features during the decoding process helps us in improving localization accuracy. The final encoder features are passed through a fully connected layer to get a classification label. For decoding, the intermediate features pass through each of the decoder layers via a dense cross connection. In the figure, the dotted blue lines correspond to each level features that are termed as FL or layer features, and the orange lines represent the upscaled feature from the downsampled layer onto the upper layer. For decoding, the intermediate features pass through each of the decoder layers via a dense cross connection. This plays the role of propagating the minute forensic features throughout the whole network and reduces attenuation. Moreover, by interleaving both lower and upper level features into the attention blocks, we are able to prioritize on global feature regions and reduce local bias. We take the 4 outputs from the first layer and add them using a deep supervision to generate the final localization map. Each of the gray circles of the decoder layers are composed of a sequence of GCA blocks and convolution operations. Each module takes as input all the features from the current layer, termed as FL, and the upsample feature of the next layer, which is termed as FG or getting feature. Now let us look at the attention mechanism in detail. All the features from the current first layer, which are FL or layer features, first goes through a 1x1 convolution to combine the channels. These are then concatenated with a residual connection for identity propagation. Next, the combined feature goes through a series of convolution and layer normalization layers. This is a bottleneck module that reduces the channel features to recombine the global and local features. The resulting feature is added to the input to enhance the global representations. This entire block is the global context framework, which recombines channels to improve the context modeling. Next, we take the upsample feature and after reduction, add it to the context features. The upstream features are more coarse and contain many unnecessary activations. This gating technique allows us to selectively filter out the necessary feature representations. Finally, the gated feature goes through a transformation metric W to generate the attention matrix. This is multiplied with the input to get the final decoder features. This was the structure of our GCA-Net. Next, we will see the training specifics and evaluation results of the model. Existing architectures are trained using millions of images, but due to hardware limitations, we could not utilize such a large dataset. For training, we used images from the Dresden, MS-COCO, and de facto datasets containing manipulated images. For the real samples, we used the IMD real dataset. For testing, we evaluated the models on existing benchmarks, ASIA, NIST 16, Coverage, and IMD 2020. A training pair is composed of an input image and its ground truth mask. Forged images have ground truth masks where white represents the manipulated pixels. Authentic ground truth masks are completely black. We spent a lot of time optimizing the training loss in order to counteract the lackings in dataset size and also to improve false positive. BCE or binary cross entropy loss works well if the dataset is well balanced. But for pixel level classification, the amount of forged pixels is definitely lower than of authentic ones. Moreover, since forged image regions are usually made up of pixel clusters, using more appropriate region-based losses can reduce false positives. We designed a custom loss function combining BCE loss, dice loss, and focal loss. BCE loss can handle pixel classification pretty well, but it suffers from overestimation problems because it weighs all data points equally. To solve this issue, We combine BCE with focal loss, which uses a scaled weighting parameter to change the loss value. This helps the network to focus more on small undetected forge regions instead of focusing on the larger regions. We also add dice loss in order to improve region estimation. For evaluating our model, we compared the AUC of uh, the pre-trained GCA-Net against the existing state-of-the-art architectures, MantraNet, SPAN, PSCC-Net on the 4 benchmark datasets. GCA-Net outperforms all these methods on the KCA and IMD datasets. On NIST, we are on par with the SOTA network PSCC-Net. However, we fall short on coverage, which is solely a copy move dataset. We think that this is due to the difference of coverages tested distributions. So we identified that our model performs relatively weaker in copy move forgeries compared to other types of manipulations. We also evaluate our model on the same benchmarks after fine-tuning on a 60-40 train test split. GCA-Net shows similar performance exceeding the different SOTA frameworks. The fine-tuning resulted in an improvement on the coverage set by 5 points, but we still rank slightly behind SPAN and PSCC-Net. Next, in order to evaluate the improvements in false positive prediction, we do a quantitative analysis of the false positive rate for both tampered and authentic images. For this purpose, we selected the negative logarithm of FPR as our metric. Since the distribution of fake pixels are very small compared to authentic ones, we chose this as our metric. We can see that for all combinations of test images comprising of either only authentic or authentic and forged, GCA-Net scores much higher values of FPR. This indicates the lower false positives. Here we have shown qualitative examples of output generated by our network on each of the testing datasets. The second rows are our predicted outputs and the consecutive rows are the ground truth. We see that our network performs very well in most cases and identifies regions with high precision. We also compare these qualitative examples with predictions against MantraNet, an existing state-of-the-art network. We use some hard samples from the IMD and NIST datasets. We see that for authentic images, our model predicts error-free results, which are complete black prediction masks. However, results from the MantraNet has considerable false positives. Next, we evaluate the model robustness against different synthetic perturbations, which include Gaussian blur, Gaussian noise, and JPEG compression. As expected, with increasing levels of augmentations, performance decreases proportionally. However, as compared with other methods, GCA-Net was far better at higher levels of blur and compression. This signifies that the network can be used for real-world applications with images from the internet that normally go through high compression levels to save on bandwidth. Next, we assess the limitations of our proposed model. Even though GCA-Net performs well on the benchmark test, there are definitely some limitations. The network fails in precise identification if the proportion of forged region is substantially larger than the authentic ones. That means images such as the one shown here, where the major portion in white is manipulated, the network cannot precisely locate the false pixels. However, it did identify that there is a difference boundary and labeled the central region as fake. So although the prediction is false, it was able to identify the difference between the two different regions. Another limitation is with high resolution images having very small forged portions, such as the one here, the network failed in localizing. The leftmost images show the network generated a completely black output, which means it was unable to identify the forged pixels. However, if instead of using the entire image, only a cropped portion is fed as the input, the network can give more precise predictions. This is shown on the rightmost zoom picture. This indicates that GCA-Net can be used as a computer-aided tool. So, in conclusion, we introduced GCA-Net, a gated context attention network composed of a novel self-attention layer for learning global context features from manipulated images. We were able to significantly reduce false positive predictions in authentic images and exhibit robustness against various real-world perturbations. Our evaluations on multiple benchmark datasets showed improved performance for both forgery detection and localization against state-of-the-art networks. In the future, we will further work on improving accuracy against copy-move samples and high-resolution inputs. We will also test the application of this network against deepfakes. Thank you.